Hey everybody, hope you're all doing well. So this is going to be the first of 3 videos. I'm going to be uh, making for the exam review, the second midterm. I'm going to cover a conservation of energy problem, a conservation of momentum problem, and then also a hydrostatics problem, since you are this upcoming exam is going to cover outcomes 2 and 3, right? So 2 basically covers all of hydrostatics, outcome 2. So you can expect to see, a manometer problem, a submerged surface problem, really any kind of problem you've seen regarding hydrostatics is fair game for that outcome on the exam. So we'll be covering one of those as well. And then outcome 3 is all the control volume conservation analysis stuff. So in this problem, we have this system, we have this river and this power plant. Basically, we're told that the plant is using flow from the river to generate power. And as it's doing this, it ends up rejecting some heat waste back into the river. And we're told here it's 50 megawatts of heat. So given these things, basically what this problem wants us to solve for is the temperature downstream the river. So the temperature at this point, call this the output, and this is the input. It gives us the temperature of the river upstream, and we just have to we'll use the conservation of energy to determine what the temperature downstream must be. So recall the integral form of the conservation of energy. So we have Q dot minus the shaft work rate minus the viscous work rate, and this equals our flux integral. So we have that whole that long energy term, remember. I'll write it all out here just for the sake of seeing it. Okay. So this is pressure over density, right, plus 1/2 V squared. And notice that this is basically just Bernoulli's equation, right? Gz. The only difference is we're adding this U term, which represents the internal energy of our fluid. And then we multiply this by our density. And then we take that velocity, dot it with the normal vector over dA. So this is the integral form of our conservation of energy. So at this point, we need to think about the kinds of assumptions that we want to make in order to solve this problem. So we'll list those out. Say assume. So the first assumption that we're going to make is that no work is being done by the system or on the system. So no work done by or on system. Right, and basically what this means, this shaft work term basically represents the work being performed on the system, or the work being done by the system, by other things, right? So say we had like a turbine in here, right, or some sort of shaft that was spinning and giving or inputting some energy into our system, right? We don't have anything like that here. So what that means is that this term equals 0. And that's due to this assumption. So the second assumption we're going to make, this is pretty standard. We're going to assume inviscid flow, right? And obviously what this means, if we don't have inviscid forces or we're neglecting viscous forces, they're not going to be doing any work on our system. So that's also 0. In addition to these, right, we're going to say it's steady incompressible, and uniform. And by now I think we all know what these words mean. This is kind of just a more technical assumption that we're making here. Because we're trying to solve for temperature, and we're given the temperature at this upstream position, the assumption that we're going to make is that temperature is the same at every point along our control surfaces. So all we're saying is that the temperature up at the top of the control surface is equal to the temperature at the bottom of the control surface. As I move along that control surface, my temperature is constant. So we'll say constant temp along control surface. And then we're also going to assume, it doesn't explicitly state in the problem, but I think it's pretty fair to assume that the river has a uniform cross section as you move along the river. So I mean, we're going to assume that the inlet and outlet areas are equal. So now that we've made these assumptions, we can jump back up to our equation here and notice, right, or remember we've already kind of made our simplifications here. So all we're going to need to do, we have this Q dot term, right? That's just the heat rate. And we're given that, we're told it's 50 megawatts. So all we're going to need to do is integrate or evaluate this integral over each of our control surfaces. So this inlet control surface and this outlet control surface. And really the math is no different than what we've been doing with control volume analysis, right? So if we assume constant pressure across the surface, constant velocity across the surface, right? And we did that, we said it's uniform. Constant height at the surface, which is also a pretty reasonable assumption to make. And constant internal energy across the control surface. So what we're basically doing, it kind of falls in line with this constant temperature assumption we're making. We're basically assuming that the energy of the particles passing through the control surface at each point along the control surface, so everywhere through the control surface, the flux, the energy flux is the same. So we have a constant energy flux across that control surface. So basically what that means when we end up evaluating these integrals is that we're going to be able to just pull this whole energy term out, and then we know, right, we're assuming incompressible. That's going to be constant velocity. That's going to be a constant. So we're just going to multiply all these constants by our area. So if we write this out now, what we end up with, we have Q dot equals. So I'm going to go ahead and just show the more simplified version. So we have that plus 1/2 v squared plus gz plus u, right? And then we have our rho VA. And this is going to be the outlet. And notice this is positive, right? Because I have this dot product here. So this v dot n, these vectors are parallel. So that's going to end up being positive. And then notice the inlet term, because those vectors are anti-parallel, this is going to end up giving us a negative dot product. So we're going to subtract the inlet contributions. So we'll write out the same exact thing. 1/2 v squared plus gz plus u. This is rho VA inlet. So at this point, we can simplify this, clean it up a little bit more. So based on our steady flow assumption and our assumption that our areas at the inlet and the outlet are equal to one another, I could show this with the conservation of mass, but for the sake of time and space on the page, I'm not going to. I think it's pretty clear as to why these velocities have to be equal to one another, right? Because if I'm assuming steady flow, we're saying that all the mass that comes in has to come out. And if the areas are equal, that means that the velocity passing through each of the areas has to be the same. Additionally, if we assume equal areas and equal densities, right, incompressible, these terms here, which are really just mass flow rates, also have to be equal to one another. So based on that, we can go ahead and get rid of these velocity terms, right? Those will end up just subtracting from one another, going to 0. And we kind of end up with just this. So looking at this now, we have this pressure term, right? So this pressure divided by density, it's kind of weird. Gravity times height, and then our internal energy. So if you remember back to thermo, or I guess just lecture, right? This pressure over density plus U, so this plus the internal energy, we call that enthalpy. We can define this. It basically represents the sum of internal energy and the flow energy within a fluid flow. But we can rewrite that pressure over density plus U as enthalpy. So recall, this is what we define enthalpy as, where the Cp is the specific heat coefficient. This P here, this subscript, just denotes that it's the specific heat constant at a constant pressure. And notice in the problem here, they gave us one 4,200-ish joules per kilogram Kelvin. So we'll use that to solve for our temperature. Ultimately, we'll plug this in for each of these. So doing that now, so we'll say H1, or sorry, this is outlet, so this is H2. H2 plus GZ2 times m dot, right? And we argued earlier that m dot is the same, so we're just going to rewrite both of these as m dot. So we have that minus H1 plus GZ1 times m dot. So notice the way we have our problem set up here, this outlet, we can say that this is at z equals 0, right? And then this inlet is at z equals 5. So we can get rid of this. And then we'll end up just solving, we'll plug in this h and solve for t, right? Because that's what the problem is ultimately asking for. So say q dot equals, so Cp times T2, and remember this T2 is what we're solving for, plus GZ2 times m dot minus, and this is just going to end up being Cp times T1 times m dot. If I plug in all of my knowns, so I know Cp, I know q dot, I'm just going to have to make sure I convert this megawatts to watts, right? So I'm going to have to multiply by 10 to the 6. I can figure out my mass flow rate. They give me a volumetric flow rate here. It's given as 2.5 meters cubed per second. And recall, right, if I have a volumetric flow rate, if I multiply that flow rate by the density, that should give me a mass flow rate. So this m dot can be rewritten as density times v dot. So I can plug that in for that, and then end up just doing algebra. I'm not going to show it just for the sake of time. But if I work through that, I should end up with a T2 of about 14.8 degrees Celsius. And remember as well, so this temperature here is given to me in degrees Celsius, but if I want to use it in this enthalpy equation here, this T needs to be in absolute units. The temperature has to be expressed in an absolute scale. Right, so if we're dealing with SI units, we need to convert Celsius to Kelvin, right, so we'll add 273. And if we want to do it in British units, the British gravitational units, we'll need to get from Fahrenheit to Rankine, and I don't quite remember that conversion off the top of my head, but you'd have to convert those to the absolute scale to use this expression. Yeah, so I think that's really it involving this problem. Make sure to check out the other 2 videos, and they should help kind of go over some of the stuff you can expect to see on your exam. All right, thank you.